genetic reduction, develops late computation, genetic manipulation, and the problem with it is it's not been done yet. Okay, it's of course we also want to have other problems. I want to mention the green ones, not competitive in sculptures. But let me just say this is what we want to achieve. Instead of having 200 chlorophylls like we have present algae, we want to have a small antenna so that each time they capture a photo, they can actually utilize it. It's a very simple concept, and I should say that it has several, probably now about 20 groups are working on it. About in the 1990s, 2 groups started on it that I started working with. One was in Japan with Mitsubishi Heavy Industries that I consulted for, and they called it in the introduction to the paper, my paper from 1989. Okay, that we can do this, and they showed some data which looked interesting, but it was not quite up to par. It does not quite do what we want to do it. I did some work at Berkeley, starting in the 1990s also, and I won't go into the details, but we looked at highlight, low light grown algae under stress conditions. They lose their antenna size, we can redo them, but the key to the whole problem was we can get a much higher photosynthesis saturation, but the problem is that the slope is down. The slope is photosynthetic efficiency. So did not work. We have done a lot of work over the years. This is some work I did with Joe Weissman again on mutants of cyanobacteria to different light intensities. We get an increase, but the problem is that the mutant was already weak to start with at the low light. It's not allowed. This is another experiment from Australia where they had some mutants reduced in chlorophyll content and increased oxygen dilution, but they were not able to show that this actually works in outdoors. And the same thing with the mutants that we developed at Microalgal and others on this. And these mutants, basically what happens when you make a mutation, you don't get one hit, you get multiple hits, and you essentially end up with a cripple. Maybe doing the thing you wanted to do, but it's not growing very well anymore. So the bottom line is that my view is that we need to do genetic engineering. I don't think synthetic biology is going to do it. This is the example of Craig Venter. Of course, everybody knows who Craig Venter is, the guy who sequenced the human genome and synthesized life recently. And he is into this game too because he has a program with ExxonMobil. Bottom line, the theory is good, but the problem is that the practice is still a work in progress. Okay? Outdoor sustainable activity has not yet been achieved. Why? It's because of many difficulties. First, a genetic alteration of the photosynthetic system. We have problems with slow growth and other problems with the mutants. Maybe we have increased respiration, perhaps not, we don't know yet, and there's going to be competition with wild type strains. So, but, bottom line, there are no other options. Okay, fast mixing, the light dilution, as I explained before, are not practical and are much too expensive. So if this doesn't work, we're not going to get the high productivities that we really will need for algae production. So, let me see, do I have another 10 minutes? Yes? Okay, perfect. Okay, start a little bit late. So what are we talking about productivity now? What is and coming back to Craig Venter again, okay, he made a statement not too long ago that we can make about almost 200,000 liters per hectare per year of algae biofuels, okay, by using his synthetic genomics, synthetic biology approach, okay, and he makes some interesting comments about that we are at the point of thinking of evolution and all parts of humanity will be impacted. I don't think it was a promise, it was said, but whatever. But then he said you can even do better by going vertical. But he has a competitor, actually, Harvard Professor Church, who also started a company on algae biofuels for claiming 140,000 liters per hectare per year. And this is from a magazine article from a couple of years ago. And you can see my prediction there for algae is about 28,000 liters per hectare per year. Okay, and they're claiming that they can basically overcome all previous limitations of photosynthesis. Let me just say that some people have taken great objections to this kind of very hyperbolic statements, shall we call them, total nonsense. This is from Paul Falkowski, who's one of the real leaders in the field, and who said that this paper by Joule with George Church and his company claiming 12% solar conversion efficiency is just horrendous, it's nonsense. If we get 3%, I would be very happy. I would be very happy too, by the way. 3% solar conversion efficiency is a very good goal, and I think it is achievable. But the problem is that these kinds of statements might be, always be very prominent, eminent people in the field are not only confusing and deceitful, they're creating expectations which we will not meet. So just as a little thing, and I should say, this whole thing also comes back to Professor Chesky in New Zealand, who published this paper that is the most, I saw that the other day, it's the most quoted paper in the literature, okay, and he pulled out, literally, I don't know where, okay, these numbers of microalgae, 136,900 liters per hectare, okay, and well, maybe only 60,000, but these numbers came out of nowhere. He had no basis for anything, but he is the most preeminent person in the field. Okay? And what happens is that people hear this kind of things. Actually, this was a company that did this even before the hype. They created the hype because they claimed 250,000 liters of oil per hectare per year. A company called Gainesville Technologies at MIT. Remember when in 1953 they did these experiments, which were very good. Here they did these experiments, which were very bad. Okay, they started selling licenses and photobioreactors. The algae first didn't grow, then they did grow, and they couldn't be harvested. They ran away, they would broke $70 million down the drain. Okay, and of course, well, this kind of stuff happens, but it shouldn't happen. Here's basically, and I won't obviously go through the details, but this is my view in terms of the best current, the near term, the long term of what we can do in terms of the boxes in red are the only ones that we can really do something about from a practical perspective, either by genetics or light saturation or oil content, and basically maybe we can reduce the photo emission size saturation to 40% loss instead of an 80% loss. That's what we have right now as a minimum. And maybe in the future we can get up to 50,000 liters per hectare per year. But I think that in the meantime 20,000 will be about right. So these are basically my predictions. And I should say, how are we going to achieve it? We're going to have to achieve it eventually by genetic modification. And I'd like to show this paper because my daughter is a co-author on it from a company called Aurora Biofuels, which have basically developed nanoperoxis as a model system, as a practical system for doing genetic improvements. And so they call it the green heat that has potential to replicate biology. And this is what we have to do. We have to do with algae what has been done with corn, with rice, with all our crop types. We have to domesticate them, and we have to use the power of domestication to increase the yields and to manage these cultures. We are not there. So, but where is the future? I would say, obviously, I like to look at the future because of my age. I like to look at it in the next 10 or 15 years. And I would say, this is one future. This was an advertisement by ExxonMobil. They spent $100 million on this advertisement, by the way. So it tells you where they are in this slide. And what the advertisement says is that we're going to secrete hydrocarbon fuels. And companies like Joule Technologies, which I just castigated a little earlier, okay, have done in Austin, Texas, where they say we can get cyanobacteria, excrete these fuels. And this has been a big piece of research now. A lot of people do this, okay. And for example, this PNAS paper a couple of years ago on excreted fatty acids, a significant size in California back in the 70s. And we used it to do wastewater treatment. They have been applied now to several of the treatment plants in California, but there are some, still some issues with it in terms of they're not really the kind of technology we want yet. They're not really significant advances over conventional oxidation forms, which are way too large, and we need to do better. And now let me just go in and say that this is basically the system that we are looking at. Just integrating anaerobic digestion with wastewater treatment. And this is what the company Microalgal that I represent. And I started with Trig Lundquist, my colleague, and Ian Worth, and a couple of other engineers, young engineers. And we have 9 ponds that we're trying to get reproducible data from. And I'll show you reproducible data. Even with 9 ponds, it's hard to come by, but we're trying. And eventually, this is the next step. We need to go into algae for animal feeds. I think that the first option is aquaculture, where we have something that is large volume and has a fairly good price. Not, $10,000 a ton, but something like $1,500 to $2,000 a ton. And I would just give you the last slide. And this is where I see the potential of microalgae in the future. If you look at the United States corn grain and soybean production, and if you look at what I see to be done in the future with microalgae for animal feed, okay, we would produce on 1 million hectares, which you see the middle column there, 1 million hectares, about the same amount of protein as being produced on 60 million hectares for animal feed production in the US, which represents 10% of the total world animal feed production, or 1% of the fuel production. Well, I'll tell you what, I take 10% of feed production over 1% of fuel production. But 1 million hectares, no matter what you use it for, would be a disruptive technology worldwide. And that is the vision and the future of microalgae technology. And what you see here in the red box is where I see this technology is applicable. It doesn't apply to Europe or most of North America, etc. because of climatic limitation. But it works just fine in India. So, summary, basically,
I'm in a conference. I'll call you back. I'll get back to you.
We've now been growing about 4 species commercially, 90% of it high-value nutritional products, and almost 99% of water, 99% produced in open ponds. We need to go to lower cost production systems, and we need to get this goal by increasing pond sizes, the scale of production, lower capital costs, but these are not enough. We need to also have higher productivities. And most critically, we need to domesticate algal space for this, not only higher productivity, but also the desired products and long-term culture stability. And with that, I will ask you for any questions. Thank you so much.